Okay, let's go for the next experiment. The next experiment is going to be Kepler's laws. Let's pay attention on the first one and the second one. The first one says that all the planets moving around the sun move in elliptical path, where the sun is in one of the focal points, right? So let's prove that today. Actually, let's try to make an ellipse, right? And try to see that actually that's an ellipse. How to prove it? Okay, let's do it this way for part one again, or Kepler's first law. All the planets move around the sun in elliptical path, right? And the sun is in one of the focal points. Okay, this is the sun right here, right? And the planets is right there. Let's say planet moves right in elliptical path. Okay, that's Kepler's first law. Remember to when we have an ellipse, right? The ellipse is formed by two focal points. These focal points are called the focus. This is called the focus, right? Or focal points, correct? For the case of the solar system, the sun is in one of these points, right? The other one is, of course, nothing, but again, today we have to use 2 points to create an ellipse. And then we have to check that actually that's an ellipse. Okay, perfect. Now let's go to Kepler's second law. Kepler's second law says that when a planet moves in elliptical path around the sun, it sweeps out, right, the same areas in the same amount of time. For example, imagine that the planet is right here at this instant, and after 2 months, right, 2 months, right, the planet is right here. Now let's see what is the area sweeps out by the planet. Okay, it's gonna be the area, correct, when we have 2 months. Let's go to another 2 months, right, in different path, right, of the planets. Imagine now the planet's right here, correct, and then in 2 months goes from here to here. Now let's find the area. If we call this area 1, correct, area 1, this is area 1 and this is area 2. This law says that area 1 must be equals to area 2, correct? The times must be the same. Perfect. Now let's prove that one today. Okay, so one of the conclusions for this law is that when the planet is away from the sun, right, in the farthest distance, the speed, right, slows down, right? The speed goes in this way, but when the planet gets closer to the sun, speeds up, right? Increases the speed, right? It goes in this way, right? In this way. That's one of the conclusions for this law. Now let's prove this law, or let's work with these two laws, correct? In today's experiment, we have the third one. We don't use it in this time, right? For this experiment, the third one says that the period of the planet's square moving around the sun is equals to the semi-major axis, right, cubed. Okay, great. Now again, don't worry about this. Let's pay attention on these two. Great. Now let's go one more time for case 1, right? Case 1, or Kepler's first law. Let's do it. Let's do it this way. Okay, great. So we have to construct, right, the orbital of Mercury. Okay, orbit for Mercury, right? Mercury. Let's go for Mercury. Mercury. Okay. Look, when we're dealing with ellipses, let's take these two. Right. This is for, let's say, Kepler's first law, right? For an ellipse, when we create an ellipse, right, like in this case, right, imagine we have these two focal points, correct? Now, also we create those lines that are very important in the construction of ellipses, right? This is called the major axis. This is called the minor axis. We are dealing with half, right? This is usually A, and A is just a semi-major axis. Semi-major right axis, correct? And the distance from the center to this focus or focal point usually we label as C, right? So C again is the focal point, right? Or we can say C is the focus. Okay, perfect. Now, How are these two quantities related? Using eccentricity E, right? Eccentricity equals to A over C. Great. Now, when let's say A is equals to, let's do some examples, right? When A is equals to C or about to C, what do we have? Well, we have that E is equals to 1. Means what? That we move C to this position, right? And we create the ellipse. And the ellipse is about, right, let's say like that. It's very elongated, similar to a line, close to a line, right? Like this, right? To a line, very close to that. Got it? Now, this is case 1. Another case is when we're dealing with the streams, right? Another case is when C is equals to 0. Means these 2 points meet in 1 point, right? And what do we have then? That the eccentricity is equals to 0. In that case, we have a circle, right? These two make only 1 point, and we create a circle, right? Okay, you can see the circle is just a form of an ellipse when C is equals to 0. Okay, great. Now let's create again the ellipse. This is a general picture. Let's go to Mercury. Mercury has an eccentricity, right? Eccentricity of 0.2. Okay, 0.2. Eccentricity, right, equals to 0.2. Okay, now for this case, again, let's create the ellipse again with these 2 points. With 2 points, imagine that's the case. I'm gonna show you later how to do it. Okay, and then let's go to the first law, because we're dealing with the first law, Kepler's first law. Once we create the ellipse, let's take any 2 points. Right? Imagine this is the major axis. This is, let's say, the focal points of Orchis. Okay, perfect. Now, let's take this distance from here to here, and the distance from here to here, right? Let's call this D1 and D2. And let's measure it in centimeters, correct? D1 is equal to something in centimeters. Imagine it's an example, right? It's gonna be 12.6 centimeters. Let's say D2, well, imagine that D2 is equals to 15.5 centimeters, correct? Now let's take another point on the ellipse. In the same theory as before, let's label the distance from one focal point to that point, and then from the other focal points to the same point. Let's call this P2, and let's call this, okay, P1. Okay, perfect. Now for P2, what do we have? We have, let's label this D3 and this D4. The same thing as for P1. So we have that D3 is equals to, let's say, what? 20.2 centimeters, let's say. And D4 is equals to, what, let's say, it's gonna be, let's say, 10.1 centimeters. Okay, now let's add these two. D1 plus D2 is equals to what's gonna be 1, what else? I'm trying to match these two. Okay, 1, what else? Gonna be 8, right? And it's gonna be 2. Perfect. And right here, this is equals to, again, just guessing numbers, gonna be to what? 30.3 centimeters. Okay, these are supposed to be the same. This is again just it's an example for this case. So D1 plus is gonna be what? D1 plus no, this D3, right? D3 plus D4, correct? Now let's prove that this D1 plus D2 must be equals to D3 plus D4. Yes or not? Yes, not. Yes, do it, check it, and please write yes or not, these are the same. If these are the same, of course, it's an ellipse. Okay, this is Kepler's first law. Great. Now let's go to second law, right? Kepler's second law. The second law. Okay, this is the first law, right? The first law. Okay, perfect. For this one, we have an asteroid, right? Taking this elliptical path, and we have the position for each month. We have month 1, 2, 3, right, and so on. We have 20. 20 months, right? So this is 1, 2, 3, 4. It's gonna be 20 months for this asteroid. Now let's take, this is the major axis, imagine major axis. Let's take any, the time for, let's say, 1 month, okay, 1 month. You can take it for 2 months, you want to more, well, let's take it 1 month. From, okay, this is the focal point, okay. Now let's see what is the time for one, what is the area where we're taking 1 month. Let me bring the figure. Look, this is the orbit of the planet, correct? Now let's take the sun. In this case, the sun, right? It goes like that. I'm gonna send you a picture for this one. Perfect. Now imagine that we're taking only 1 month. Let's take, imagine from month 2 to month 3, right? Let's connect these two to find the area sit up by the planet. And let's go to another 2 points. Let's say which point you like. Okay, let me see. 16, 17. Imagine this is 17, right? This is 16. Let's go to 16 and 17, right? Like that. Okay, this is from month 16 to 17. This is from 2 to 3 months, for example. Okay, or yeah, let's take it like that. Perfect. You can take from 3 to 4. It's up to you. Okay, 3 and 4. And then looks right here we have that this is a graph paper. So we have, look, squares right here, squares. Right, we have squares right here. Okay, now let's count the squares. Imagine that we label this area 1 and this is area 2. Right, now let's label the, let's count the squares. Look, in this way. Imagine that this is the, let me make it larger. This is the graph paper like this. Okay, perfect. These are the squares, right? In this way, imagine. This is actually right there, right? Perfect. Great. Now imagine that this line goes in this way. Imagine. Like that. Great. Now let's count the squares. In this section in between, right? We're counting the squares inside. In this part is the whole square, right? This is 1. This is 1. This is 2. If this is more than half, let's count it as 1. 1. This is half or more. Okay. It's gonna be 3, 4, 5, 6. This is less than half. This is less than half. Don't count it. Right? This is less than half. Don't count it. This is, of course, more than half. This is gonna be 7, 8, 9, and so on. Okay, let's do this the same procedure for these 2 areas and count how many squares, right, do we have. So now be area 1 equals to, imagine 100 right squares, and A2, imagine you have to do it. Let's say 98 right squares. So these 2 are very close. Remember, we're getting an approximation, right? These are very close. That is, the difference is no more than 5. Right, to mean that areas is, they're the same areas, correct? So again, let's see, the area 1 is equals to area 2, yes or not, for this, for yes or not, for this experiment. Again, you have to count them, right? And that's gonna be this experiment. I'm gonna show you how to do it in a moment. Okay, for today's experiment, we need a piece of paper, right, like this, a cardboard. You can use this one, right, the size of the sheet of paper, like in this case, could be larger, it's fine, or you can use this foam board, right, like this. Okay, that you can buy it in a store, right? Okay, great. Let's do it for today's experiment, right? Let's go to Kepler's first law. Let's create an ellipse, right? Let's do it. Let's create an ellipse right here, let's say. Okay, great. Now let's see. for Mercury, remember for Mercury, what happens? For Mercury, we have that eccentricity equals to 0.2. Okay, that's Mercury. Perfect. Now, let's try to see how long is this sheet of paper. This is gonna be what, 28, about 28, and right here is about 21. Okay, let's make, for example, remember eccentricity, remember, is equals to A or C over A, correct? Remember, this is the ellipse right there, like this, right? And this is C, and from here to here is A, correct? So the eccentricity is C over A. Let's take A, for this example, A equals to 10 centimeters. If A is 10 centimeters, what should be a C? C, remember, is equals to EA. So it's equals to 0.2 times 10 centimeters equals to 2 centimeters. So for today's experiment, right, for Mercury, let's take A to be 10 centimeters, right? So C is gonna be 2 centimeters. Okay, let's do it. So let's go to the center right here one more time. Okay, let's center this ruler, correct? The center is gonna be around 14 because it's around 28. Okay, 14. Now 14 plus 10 is gonna be 24, right? And 14 minus 10 is gonna be 4, right? So look, from this point to this point, from the center is gonna be 10, and right here is gonna be another 10. Perfect. And we found that C is equals to 2 centimeters, right? C is the distance from the center to the focal points, right? Right here, this is 2, and this is where? This is 2. Oh, let me see. No, this is 2 right here. Sorry, it's gonna be 2 at this point, and right here is gonna be another 2. Okay, perfect. So these 2. I made a mistake with that. Okay, that's fine. Okay, now let's use these 2 pins. These 2 pins, or we can use nails, more like nails like that. Okay, it's up to you. Now let's go to also we need a thread, right? Like this one. Okay, to do it. Perfect. Now let's find the distance again. This is the center. Okay, this is for you, this is 0. Okay, for reference so far. Okay, so let's go from here. Right, this is one focal point. Now to get the right distance, let's put this pin in the farthest distance, which is that one right there, correct? And now let's use this thread to create the distance. Okay, let's do it. So what do we have again? We have this position right here. Okay, perfect. Let's make a knot in this way. Great, it's coming. Okay, and I did it by myself, right? Now let's go back and place the pin in the position of the focal point, right, which is that one. Remember, we have the focal points right there. Perfect. Now let's go back and place the thread in this way. We can use a pen, so it's easier because we make any mistake, we can erase it. Okay, perfect. Now let's mark the path of this ellipse, right, in this way. Very nicely, be careful. Okay, yeah, oops, see what happened right here? Just go back. Don't stretch too much, right? Go back, right, and complete the. This stretch a little bit, all right? Also, if you pull it hard, right, these are movable, right? You can move it, or you can stretch it extra, right? Try to make it smooth, right? The path, right? Very smooth, correct? And you create the orbit of Mercury, right? This is the orbit of Mercury. Yes, and what happened? Well, just label, right? This is for Mercury. Mercury, make it very nicely. Mercury, right? What else? Eccentricity equals to 0.2, right? Just the data, right? A is equals to 10 centimeters, and C equals to what? 2 centimeters, right? This is for Mercury. Now let's do another one because you are so happy. Because it looks like a circle, right? Let's create something different, more elongated, like an ellipse, right? Let's use the other side of the piece of paper, correct? And now let's use this data. Let's use A A equals to, let's say, what is the maximum distance right here again? Let's say A equals to 12, okay, and C equals to, let's say, 8 centimeters. Let's see what happens. Okay, 8 centimeters. Okay, let's do it one more time. This is for part B, right? Case 1. Okay, let's do it one more time. That's gonna be 12 for C, for A. Okay, imagine the center again is gonna be 14, more or less is 14. 14 minus 12 is gonna be what? 2, and 14 plus 12 gonna be 26, right? Imagine. Okay, so we have then, and then what about C? C is gonna be 8. Where is 14 minus 8 is what? Is 4? Oh wow, it's 4? Really? 14 minus 8? No, it's not 4. It's what? It's 6. 6, right here, 6. Okay, and 14 plus 8, 22. Okay, perfect, 22. Right. These are the points, the new points for the ellipse, the new ellipse. Okay, let's do it. So we have the pins one more time. We have one right here, right, and one at the farthest point. Okay, this one. Okay, remember, just you can label if you want to. Don't forget it's C1, right, and C2, right. This is the center, 0. Okay, oops, perfect. Now let's take another thread, right, like this one. Great, let's do it. Let's do it because we don't have too much time. Okay, imagine.